Let's talk about reading potential energy curves. So a potential energy curve is just a plot of the potential energy U for a system as a function of position. So this potential energy changes on the particle when it's in one-dimensional motion while a conservative force acts on it. So on these plots, we have potential energy on the y-axis and we have position on the x-axis. So we're going to get something from the slope here. And we know, again, we're graphing the function of potential energy with respect to position, x. And then from earlier in this chapter, we know that the change in potential energy as a function of position is equal to the negative work done on the object. So if we remember that work is equal to force times displacement times the cosine of theta, we get that the change in potential energy is equal to negative force and then multiplied by displacement. So here, if we solve this equation for a force, what we get is the change in potential energy over displacement. So here, what this tells us is that when we look at the slope here, which is just going to be change in potential energy over displacement, or delta U over delta X, we are going to get a negative force. If you multiply both sides of this equation by -1, you get du over dx equals negative force. So the negative slope of the graph is going to be the force. And this is really, really important to remember here. Also, if we take the derivative of the potential energy function with respect to position, we get the negative force as well. So you take the derivative, slap a negative on there, and you then get your force. So if we graph the force, then from the potential energy graph, it's going to look something like this. So again, when we're looking at that force, it's the negative of the slope. So if I have something like this, our potential energy graph with respect to position, here we want to look at what's happening to slope. So at this position, this part of the graph right here, so until about x equals x1, we have no slope here. So we start at a force of 0. Then we start with a negative slope, which means that we have a positive force, okay? Negative slope means positive force because the slope is the negative force. Now down here at x equals 2, again, we have a slope of 0, so that means we have no force at x equals 2, and then we start getting a positive slope, which tells us that we have a negative force. At x3, we again have a slope of 0, so we have no force at x3 or at x4. We can see that, but between x3 and x4, again, we have a negative slope here, which means we have a positive force. And then between x4 and x5, we have a positive slope, which means negative force. So if we look at something like this, again, we have no force, so force equals to 0. Here, where we have a slope of 0, at x equals 2, so we can see that we have a slope of 0 here. At x equals 3, slope of 0 here. At x equals 4, slope of 0 here, and then after x equals 5, slope of 0 here. And then as we go down here, this is a negative slope, we have a positive force right here, and then here we can see that the slope is increasing, which means that the force is increasing. Here we have our largest positive force, and then it's going to decrease back to 0, which is why we're coming back down to 0 here. Here, our slope is lower in magnitude, so it doesn't get as high as here, but because it's a positive slope here, that means it's a negative force. And then here, we have a slope that is negative, so we have a positive force here, and then here we have a positive slope, so we have a negative force here. So you can kind of see how we could get a force graph from our potential energy graph. Now, if we're trying to find kinetic energy from potential energy graph, we have to remember that mechanical energy of a system has a constant value that's given by this right here. Mechanical energy is equal to a combination of potential energy plus kinetic energy. So from this equation, we can get an equation for the kinetic energy function. We get kinetic energy is equal to total mechanical energy minus potential energy. So if we know that the total mechanical energy has a constant value, which we know from conservation of energy, if you have no non-conservative forces, then we do have a constant value for mechanical energy. So suppose it's something like 5 joules. It's represented by a horizontal line drawn on the potential energy graph. So you'll see an example of this, and they will give you information in these problems to find the total mechanical energy. Once you find that, then you draw a horizontal line at that point. And then you can find kinetic energy on the curve by subtracting the potential energy from the total mechanical energy. So an example of this here would be, they would say something like the particle is released from rest at x1 equals 2 meters. So what this tells us is that because our particle is released from rest at x1, rest means no kinetic energy. So what that tells us is that at this position x1 right here, which is 2 meters, that means that we have all potential energy. So our potential energy is equal to our total mechanical energy. You would come up here to this position x1, wherever we're at on this potential energy curve, and you would draw a horizontal line at that point. So this means, like I said, that at 2 meters, all of the particle's energy is in potential energy. You would draw a horizontal line from the potential energy curve at that point to represent the total amount of energy. Another example would be at x3 equals 6 meters, the particle has 2 joules of kinetic energy. So you would come here to this x3, which is 6 meters. And here I would see, okay, looks like I have 3 joules of potential energy. And then it says the particle has 2 joules of kinetic energy. So I would then add 2 joules in order to get my total mechanical energy, because I know total mechanical energy is equal to kinetic energy plus potential energy. So that means that my total here would be 3 plus 2, which is 5. And then again, I would draw a horizontal line at that 5 joule mark, because that is my total mechanical energy, and that is not going to be changing because of conservation of energy. So we would add this amount of energy to whatever potential energy the particle has at that point to get the total energy, and then you would draw a horizontal line at that point to represent the total energy. So once we do that, you can see here that with both of those examples, I was given the total mechanical energy, and I can see that I've drawn a horizontal line at that 5 joules, because again, the total mechanical energy is not going to be changing. Now, because of this, we get these things called turning points. So a turning point is a place that we can't go beyond. Now, the whole key here is that kinetic energy can never be negative, because v squared can't be negative. So we know kinetic energy is equal to 1/2 mv squared. Mass isn't negative. Velocity could be negative, but a negative times a negative can never be negative. So because of that, kinetic energy itself can't be negative. So because of this, the point where that mechanical energy line meets the potential energy curve, we call this a turning point, which is like this point right here, okay? So what happens here is as the particle moves from, say, our position x2 to our position x1, which is where our turning point is located, it slows to a stop, because we can see that the difference from this potential energy to the mechanical energy, that's going to be our kinetic energy. So we can see here that kinetic energy is decreasing, 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 and then that means it's slowing to a stop here, and it can't move any farther left because, again, it can't be negative. We can't go above this total mechanical energy line. So because of that, instead it starts to move back to the right. So it turns around, which is why it's called a turning point, and it moves back to the right. So we also have these things called equilibrium points. So in these examples, we have different total mechanical energies. So I know that I've been talking about a total mechanical energy of 5 joules in our last examples, but here it's when we're changing the total mechanical energy amount that we get these, what we call equilibrium points. So You'll see what I mean when we start explaining. So if say my total mechanical energy is 4 joules, so I draw a line here at 4 joules. If I get to this plateau right here, this is called a neutral equilibrium. All right, neutral equilibrium. So we have a system's mechanical energy is equal to its potential energy in a neutral equilibrium. So we can see here, our total mechanical energy is that 4 joules. And then at this plateau right here, beyond x5, we can see that that's what our potential energy is equal to. So all of the energy is in potential energy. Now here, the particle has no kinetic energy and no force acts on it because we can see that the slope here is 0. So that particle must be stationary. This is called a neutral equilibrium. An example of this would be like a marble on a tabletop, right? There's no forces acting on the marble to the left or to the right, so that marble is in neutral equilibrium. Now, instead, if we have, say, our total mechanical energy of 3 joules, and we draw, again, our horizontal line right here, this point right here is called an unstable equilibrium. Now here, again, our kinetic energy is equal to 0 because we can see that total mechanical energy is 3 joules, and our potential energy is also 3 joules. So all of the energy is in potential energy. But we can also see that although our force is 0, it's very precarious here, right? Like if we move a little bit to the left or a little bit to the right, we now have a non-zero force, which is going to then force it in one of those directions, and therefore we will then start moving. So we have a kinetic energy of 0 here. Force is 0 because the slope of this curve at this point, x3, is also 0. However, if it's displaced slightly in either direction, a non-zero force is then going to push it farther in that direction, and then the particle will continue to move. So if we have something like a marble on a bowling ball, right, it could balance there, but it's very precarious. So this is an unstable equilibrium point. Okay, and now for our last couple examples here, we have a total mechanical energy of 1 joule. So now we're drawing our horizontal line at this point right here, and we have 2 different equilibrium points. So our first one is at this point right here, x4. So this is called a stable equilibrium. Now here in a stable equilibrium, our particle is stuck. All right, it can't move either direction. It can't move left or right because to do so would require a negative kinetic energy. Again, we can't go above this total mechanical energy with our kinetic energy. Okay, so if you push it slightly to the left or to the right, a restoring force would then push it back. So this would be like a marble in a bowl. And then last but not least, we have this thing right here called a potential well. So again, we have, say, our particle at x2 or something like that. Our total mechanical energy is 1 joule. So you can almost see that our particle is kind of stuck right here because you have a turning point here and a turning point here. So the particle can move somewhat, but only part way to those turning points.